Hi, I'm Chris.
And I'm Terry. Welcome back.
Welcome to the Chris and Terry Show, as people have started calling it. Today we're talking about principle number 2 of the neural engineering framework. So last lecture was really focused on representation, both in 1D and 2D, which is principle number 1. And today we're moving on to computation or transformation, whichever kind of terminology you prefer, to understand better how you can actually perform sort of interesting changes in the information instead of just representing and spitting it back out like we did with principle 1. So let us jump right in. I will share my screen. Right, so as I mentioned, moving right into principle 2, I think we'll take a little bit of a different approach this time. That is, we want to motivate principle 2 by thinking about an example. And where will we turn to this example when we look at dynamics, principle number 3 in the next lecture. But let's sort of start thinking about how can we, obviously we don't want to just represent information as we've looked at so far. We actually want to do things with that information. So what are the kinds of things we might want to do? And here's a simple example. So think about working memory. This is something that is very important to cognitive modeling in general. And if we characterize what working memory is, it essentially means that you're shown some information, the information goes away, but that cognitive system can retain that information over some period of time. And you also want to be able to manipulate what you retain. So you might want to erase your memory, you might want to load new things into memory. And all of these are going to require different kinds of computations. Some of the computations are over time, and some of the computations are sort of more of a feed forward or control variety. So in summary, we want a circuit that stores some kind of input state. We want to be able to clear that input state. So that means the storage is going to be controlled. And we're going to want to specify this at a high level, right? So you can think of this as like a programming language if you want. The language that we are using at the high level, as I mentioned before, is dynamical systems theory or control theory. And that means that we're going to write this function down using a differential equation. And so here's a simple differential equation that will actually do something like what we're looking for. So just to sort of quickly explain what's going on here, we're saying that we've got an input, which is u. We have some state, which is x. And typically in working memory, what we really want to do is store that state x over time, right? So that's going to mean that the change in x over time, x dot, is going to be equal to 0, right? So we don't want to be changing the state once we've got it put into the system. And if we don't change the state over time, it means we have a memory. We have something sitting there. When we're trying to store information over time, so suppose for a minute that we are being shown a number, a digit, let's say, that's going to be our input u, and we're starting with x equals 0. If we show u, then that over some period of time, let's just pretend B is an identity matrix. So we're really just loading whatever u is into the memory. So we're going to show the u for a while. That means that the change in x is going to be equal to u. And once we take u away, then x dot will basically go to 0 because we're going to pretend everything here is 0. But when x dot is 0, x is going to be storing whatever it's been shown to this point, namely the digit that we had shown it, for instance, which is great. We want to store that information over time. But eventually, we want to be able to clear the information, as we set up here, right? We want a working memory that can be cleared. And that means that we're going to want to vary this value alpha. So alpha starts as 0. And when it's 0, we're going to store the information. And if we want to forget the information, that means that we're going to want alpha to be equal to a negative number, because then we'll be multiplying it by whatever the state is and essentially subtracting that away from the current value of x. So if we make this a big negative number, then we're very quickly going to essentially erase what's in x. X dot's going to be some negative number. It's going to get rid of everything that's in the memory, and we'll go back to 0. And then we could load a new thing in. If we didn't have this kind of control and we just loaded a new digit in, we'd start getting a sort of mixture of the two digits that we were trying to represent, perhaps. Then that might not be the memory we actually want. So instead, we want to have this kind of controlled memory. We're able to either set a to 0 in order to load something in, or we can set, or alpha rather, to 0, or we can set alpha to a negative number and kind of erase what's currently in the memory. Now, what this introduces is something pretty important. This looks a lot like representation when we're just loading stuff in, but this now is going to require a kind of computation. We have to multiply some number alpha, which is changing over time, with some state x, which is also potentially a function of time. And that kind of multiplication is not representation, right? We really need another principle. We need to figure out how can we compute functions of our state variables rather than just representing our state variables. So that's what we're going to focus on with this lecture, looking at how do we compute or transform information over time. Principle 2, transformation. Now, if you might recall from the last lecture, in words, Principle 2 is something like, we have the same nonlinear encoding that we do for Principle 1, and then we take an alternate linear decoding of the information that we've encoded. So what exactly do we mean? So if you remember back to Alice and Bob, we have two neurons that have different tuning curves, and therefore they generate different spike trains for a given input. And then what we did is figure out what Charlie could know about Alice and Bob. The Principle 2 has exactly the same encoding to start. So we can say, here's the same input signal we saw before. Here's the function that we're going to want to compute at Charlie rather than just reproducing it. But, Alice, who is the on neuron, and Bob, who is the off neuron, are actually going to generate exactly the same spikes that they generated last time. But the difference now is going to be on the decoding side, right? Instead of just having our filter and being able to add those filters up in order to reproduce the signal, we want to have filters which are actually going to, compute some function. And here the function we started with is a simple linear function, just 2 times the input. And you might recognize these as being a little bit stretched out. Really what we've done is essentially multiply these by 2. And we multiplied these ones down here by -2. And in so doing, we can do the same sort of summing up now that we did last time. And that gives us an estimate of 2 times x. So what I mean by alternate linear decoding is because we're computing a function, which is 2 times x, all we did is instead of multiplying by +1 and -1, we multiplied by +2 and -2. And again, we get an estimate here, which is an okay estimate of that dashed line. It's not great, it's definitely got error. But you can imagine that just like before, as we add more and more neurons in, we can get a better and better representation of the function that we're trying to estimate. So this is a good start, but clearly just a linear function. So looking just at the function space, right now we're sort of forgetting about time. We're looking back at these tuning curves that we've seen before for Alice and Bob. And here, this gives us a sense of trying to estimate a linear function, right? So the perfect linear function would look something like this. But when we sum these two up in the right kind of way, right, so -1 and +1, we see that we can get an approximation to a line, but it's not great. But that's essentially representation. All we're doing here is essentially changing what those weights are. And to give you a sense of how you can compute a nonlinear function, let's just suppose that instead of subtracting and adding in this particular way, we're going to subtract and add in a different way, namely add both of the functions together. And if we do that, then we get this weird sort of W-shaped function. But the interesting thing about this W function, this might not be a function we ever want to compute, but what it is clearly a nonlinear function of x, right? So you're not going to write in any linear equation, which is going to give you that kind of output. And so this suggests that even though we're only using a linear decoding, we can still compute nonlinear functions. This is something that we're going to look at a couple of times over now, where we will look at a couple of examples of computing linear functions, which are clear and straightforward. If you can do representation, linear functions are really quite easy. You just multiply by the linear function you want to compute, like we saw on the previous slide when we multiply by 2. Or you can come up with all kinds of interesting different sorts of weightings and get these wide variety of nonlinear functions. So to give a little bit more intuition about a function we might actually want, we can again look at estimating a function, and here seeing what the effects of having increasing numbers of neurons might look like. In this case, the function that we're looking at is y equals x squared. So you can see for our very first estimate with 2 neurons, not a great fit to y equals x squared, where what we're really trying to do is trying to estimate a function something like that. But just like with representation, as we increase the number of neurons, so this is 8 neurons and eventually 30 neurons, as the number of neurons goes up and we find the optimal decoders like we saw just for representation, but now instead of optimizing to represent and reproduce the input, we're optimizing to compute some function of that input. Eventually, with 30 neurons, you can actually do quite a good job of computing a quadratic function, right? So this really does look like x squared. Still has some error in it. Obviously, it's not a perfect reproduction of x squared, but this sort of adding of more and more neurons, increasing the quality of the function representation is something which is sort of well established in the NEF. And we can even look at exactly what functions you can do the best job of representing. Just to give you a quick hint, essentially broad polynomials turn out to be something that are really good to represent with tuning curves that have these sort of broad kind of tuning like we see here. So this kind of brings us to principle 2, computation. Now we can look at what that might look like over time. So suppose that we are trying to compute a function. Again, we're going to look at the function y equals x squared. So to test this function, we want to input some input over time. Here we're just putting in this ramp, right? So this ramp is going from -1 to 1. As we go from -1 to 1, we've got a population of, I don't know, 20 or 30 neurons here, and they're generating all these different kinds of spike trains. To decode those spike trains, we're going to do exactly what we saw in the previous slide, where we're going to calculate some sort of decoding weight, DI, for every single one of those neurons. And we're also going to filter all of these neurons by postsynaptic current. This is a linear, simple linear filter. And if we do that, then we can see that as we ramp things up over time, so this is time down here, we are getting an estimate, albeit quite a noisy one, of this function x squared. And of course, we can do things like see what is the nature of this noise, right? What happens if we change the time constant? So if we make this postsynaptic current longer, is that going to smooth things out? What are the consequences for responsiveness and all this exact same things that we talked about before? So really the nice part about principle 2 computation is it's essentially exactly like principle 1. If you felt like you understood principle 1, then in a lot of ways you really understood principle 2. And just to be a little bit more explicit, when we're finding these decoders D here, what we're doing is solving pretty much exactly the same equation that we saw before. So before we saw that we had a difference between x and x hat, and now we're going to solve f and estimate of f, right, over the same domain. So all we've really done is stuck in some functions of x instead of having x and x hat. So we're optimize that. We'll be representing our f of x hat as a sum over a bunch of our neural activities, right? All these spike trains times some decoders, which are decoding some function x. And those decoders are exactly what we're going to be finding by minimizing this error between the function we want, this one here, and our estimate of that function, right? So this all looks really familiar. It's very analogous to what we saw where we just had x and x hat. And the optimization problem's the same. All we've really done is stick in a different kind of function. And the exciting and interesting and sort of surprisingly powerful thing is that that function can be essentially anything. How well we'll represent it will depend on the function and the number of neurons, etc. But the methods for doing that representation follow quite in a fairly straightforward way. As you can see down in the bottom corner, we've got time to get our hands on and look at how this works in Nengo and see exactly what it's like to build some circuits that are doing something more interesting than just representing what you stick in. So I will take this opportunity to turn it over to Terry.
Back into Nengo again. We were starting all fresh, so I've just started up Nengo. And what we're going to do is start a new file. So I've clicked again up at the very top here. We're saying what file we're on. Click on that and say we're going to go on to, I think we're now up to example 5. And what are we going to do with this model? So it's actually what we're going to build is pretty close to this first default model, but let's build it manually anyway, just to make sure that we know what we're doing. First 2 lines of any Nengo program are always this import Nengo and then make the model. So model is Nengo network. And now we're going to put a bunch of things into that model. And the first thing that we're going to add is a group of neurons. We're calling this group of neurons A. Oops, and I need to be able to spell. There we are. We need to pick a number of neurons. I'm going to pick 50 neurons. And we need to know what the dimensionality is that those neurons are representing. So those neurons, there's 50 of them. They're working together to represent one value, might be in the cases that Chris has been talking about. As we mentioned before, if I don't specify anything else, it defaults to doing leak, integrate, and fire neurons, and it randomly assigns the encoders and gains and biases to those neurons such that you get a wide distribution of tuning curves. Okay, so there's our neurons. We're going to have some input to those neurons. So the input is a node, and we're going to connect the input to the neurons. Okay, so that's all basically what we've seen before. And just as a reminder, if I now go ahead, I can pull up a slider, I can pull up some spikes, I can pull up a value plot. I suppose I should get rid of this value plot that was already there. And if I press play right now, and I change my input, my neural activity changes, and then this value plot, the value plot that I right-clicked on here, Nengo has sort of a built-in default of do the representation trick that we talked about last time, find me the decoders that will allow us to decode out whatever the input was. So that was the representation aspect that we talked about before. What we want to do here is we want to create new decoders to compute some other function, because that was sort of the goal of this computation aspect. If we're going to do that, I'm going to need some place to put the result. So we're going to make one of these output nodes again. And this is going to be a node that does nothing, but it does store a one-dimensional value. So that's these little tiny nodes that we made before. And I can make a connection from these neurons, Nengo.connection from A to output. That's somewhat similar to what we did in the last example. So in the last example, when we were playing around with learning over time, we did sort of a connection from A neurons to output, and then we had to specify a weight matrix, because in order to, if there's 50 neurons and there's one output, then I'm going to need a 1/50 weight matrix. That's not quite what we're doing here. What we're doing here is we're saying, look, don't treat A as a bunch of individual neurons. I want to think about A as it's representing something, and just make a connection that is taking the value being represented and feed that into output. Okay? In the underlying simulation, A is just a bunch of neurons, and so there is just a set of connection weights there. But what I'm doing here is I'm just telling Nengo, look, I don't want to specify the connection weights. You figure it out for me. And I haven't told it yet what function to optimize those connection weights for, so it's going to default right now to the identity function. Right, so let's just first confirm that that works, and then we'll get it to do a more interesting function. So I say that. I do this. Okay. So when I press play there, Nengo went ahead and found a set of connection weights to go from these 50 neurons to this one output that does a good job of taking whatever these spikes are and converting them back into a representation of what the input was. So again, that's exactly the same as the representation trick. And now what we're going to do is we're going to do a slight modification to say, hey, I don't always just want an identity function. I want some other function. All right, so let's make a function, say squaring.
Terry, if I could just jump in for a sec. I'm guessing that some of the keen-eyed watchers will notice that the output node looks slightly different than the value plotted from the A node. Maybe it would be worth sort of explaining why there's that difference.
Fair enough. That is a good point, because yes, these are slightly, I mean, if you overlay them on top of each other, they are pretty much the same value, but this output seems less noisy than A. What's going on there? What's going on there is every time in Nengo we are trying to decode from spikes and try to get some value, we generally also figure that spikes tend to involve some sort of synapse, and if there's some sort of synapse, then that's going to tend to involve some sort of postsynaptic current. So when Nengo is taking these spikes and making this plot, it is also, it is both doing the weighting, the sort of the weight each value by whatever the connection weight is that it solves for, but then it's also doing that weighting over time, or that linear function over time, that is the postsynaptic filter. We can see that if I right click on this plot and say set synapse, we can see that the default that it's using is a 10 millisecond filter there. If I say 0, all right, so if I turn off that filter, whoops, oh, helps if I actually have working code over here, so we'll get rid of that. Nope, and I've managed to confuse Nengo. Excellent, this is a beautiful example of, yes, sometimes Nengo gets confused. And so what I'm going to do is I'm just going to press reload. And I reloaded it, and it works fine. All right, so important safety tip when using Nengo: if things are going wrong, just like everything else in all software whatsoever, just hit refresh, close it, restart it. But if you really want to, but you know, the standard, just reload the web page, because it's in a web browser, that tends to work well. All right, back to what I was trying to show. We have a bunch of spikes. This plot, this was the value plot. The only thing I've changed is I've changed the postsynaptic filter to being one with 0 milliseconds, so there's no filter happening at all. So now this output, we're not doing the smoothing over time, and you'll see that it still works, but it's very, very, very noisy. Right. I'll put it back to where it was. Whoops, wrong plot. Set synapse, that's what I meant, 0.01. Okay, now it's back where it was. All right, so that is happening whenever you have one of these plots. There is a synapse that is automatically being applied, or synapse value that's automatically being applied there, just to smooth that over time a little bit. The same thing, so why is it that this plot is the same as this plot? Fine, they both have exactly the same, they both have the same filter going on, but then there's one extra thing happening here, and that is there's also this connection from A to output. Anytime in Nengo you make a connection, there is always a synapse involved, and the default is a postsynaptic current of 5 milliseconds. You can do much more complex synapses. You can do alpha synapses. You can do like weird giant LTI systems as synapses. The default is just an exponential decay, because that's sort of the simplest. And the default is about 5 milliseconds, which is sort of at the high end, or the fast end of what you find in brains. If I get rid of that synapse, now these two plots should look pretty much the same. All right. What was happening, the reason this output plot looked smoother is that there was 2 different filters happening at once. There was one 5 millisecond low pass filter happening here, and then another 10 millisecond to make the display. Okay, so yay, more details of how Nengo plots things. But it is important to keep in mind, anytime you do a connection in Nengo, there is some sort of synapse potentially involved, and that's generally useful when we're working with spiking neurons. Cool. But again, we're still in the situation where we're just representing the value. We want to come up with, hey, we want to tell Nengo, hey, there's some other function I want you to approximate. Fine, the default is the identity function, but we want to be able to do other functions. So what we're going to do is we're just going to use normal Python syntax to define a function. So this is just the normal way in Python you define a function. I'm calling it a function square. It's a function of x. X in general can be a vector. In this particular case, it's a one-dimensional vector. And I'm going to say, please return x squared. Okay, so that's just how in Python you define a function. You can define any function you want in there. We will go and see some more complex examples. It's just arbitrary Python code. And basically what's going to happen is now we're going to tell Nengo, use the neurons to approximate that function. And so all we do is when we make the connection, we tell it what function to approximate. Okay. So now when I press play, Nengo, when it goes and finds these connection weights from A to the output, instead of trying to find the representation, the connection weights that will do a good job of representing A, it'll find the connection weights that will do a good job of approximating this function. And I run that. And now what have we got? Ooh. All right, well, if I feed in a 1, I get out a 1. If I feed in a -1, I get out a 1. Feed in a 0. Oh, I can click on this slider and actually type a number in. So let's do that. So I feed in a 0. I get out a 0. If I feed in a 0.5, I should get out a 0.25, something like that. Yeah, somewhere around that range. And -0.5 should be similar. All right. So, and the only thing that's happened here is we just have a different set of connection weights from A to output. Okay. We can play around with lots of other functions. So another function that I like showing, and also sort of as an example that you can put arbitrary Python code in here. This is nothing to stop us from doing something like this function. If x is less than 0, return -1. Otherwise, return 1. Okay, that's also a function. This is going to be a harder function for neurons to approximate, and we'll sort of see that. So if I feed in a number that is up here, well, any number somewhere in this range here, I'm all getting outputs that are sort of near 1. I go down here, all my outputs are sort of near -1. I go in the middle. All right, so certainly this is not quite the behavior we've asked for. The actual function that I've defined only outputs -1s and 1s. It never outputs a 0, right? All right, and so what we're seeing here is that the neurons are doing a poor job of approximating that function in this sort of middle range. Okay, we found the best job that they can do, but they're not doing it well enough. If we want this to do it better, well, one easy thing to do is just have more neurons. So at the moment we have 50 neurons. Let's go up to 500 neurons. Okay. And now, pretty much any input up here, we are really good at representing 1. All right, for all of those values, we are rock solid at 1. For all these values down here, we're pretty good at -1. So we're much better at that. We still have some small little range around 0 where we sort of smoothly transition. So instead of this function itself is a really sharp step function, we're instead getting sort of a smoothed version of that step function. If I'm working on if I'm building a cognitive model and I really need a really good step function, maybe I need more neurons. Maybe this is a good enough step function, right? Sometimes it's nice to have just a smooth version of the function. But the general tricks are going to be things like if you want to do a better job, then you want to increase the number of neurons in your that you're decoding that information out of. There are also some fun things you can play with for certain types of functions. Say, oh, maybe you want to adjust your neuron tuning curves to make it better at this particular function. But that sort of thing may come up later. But this general idea will let us approximate whatever functions we feel like. One thing that I should also mention in here is so far in all of our examples, we've been assuming that our ranges of inputs are between -1 and 1. That's a parameter on our ensemble. So just like, we have a bunch of defaults for the neuron properties, we also have a default for, that range of inputs that it can work on. The default, so the parameter to adjust this, the default is a radius of 1. What does that mean? That means this is a one-dimensional input. So a radius of 1 in 1 dimensions, that's going to mean the input is values between -1 and 1. Okay. If we had dimensions of 2, then that would be saying the input is all the points inside a unit circle of radius 1. Okay. Again, these are things that we can adjust and modify if you have some other space that you want to handle as an input, but those are the defaults. But say I wanted an input to have a radius of 10. Right? So now I'm inputting values between -10 and 10. Then I would just simply set that as my radius. And if I don't have to change anything else here, I can go ahead and run this. But now I'm in a situation where even though my inputs and outputs are across a bigger range, my user interface is between -1 and 1. And that's why you can right click on the user interface and also set its range. So we can go from -10 to 10. Same thing on these plots. We can set the range -10 to 10 and set our output. Oh, actually, we don't want to change since our output is still from -1 to 1. So we don't want to change that at the moment. But now you will note that our values are from -10 to 10 instead of -1 to 1. Importantly, and the reason I sort of like this example at this point is you'll notice that nothing has changed here. Like the plots look exactly the same as when I was doing things between -1 and 1. Now that I switch things to -10 to 10, everything sort of looks the same as we've scaled out. And that's exactly what's happening internally in order to do that sort of scaling. This radius really becomes just a parameter that sort of says, that helps scale things when we're making inputs and creating graphs. So there's no biological significance to this radius parameter. It's much more about the mapping between the values that we're representing and the activities itself. All right. Anyway, all of that said, yes, you can go ahead and use values outside of the range -1 and 1. Just make sure to set the radius correctly. Back to you, Chris.
Great, thanks, Terry. So now we've seen a hands-on example of computing some functions. One's, a little bit more challenging, in fact, than this x² one that I've looked at here. But you might have become a little bit curious about why we keep talking about a single population of neurons and sort of like we're computing a function right out of this population of neurons. And this is not how we typically think about neural networks, of course, right? We think of neural networks as being, layers and layers and layers of neurons with all these connections between them, and that the functions are actually being computed in those layers. So let's move in that direction where we're actually building circuits instead of just having a single layer and sort of decoding something out of the information in that layer. I think this is typically a little bit more like what people think of when they think about neural networks. So let's start by thinking about the simplest possible circuit. This is going to be a circuit we call a communication channel. The purpose of this circuit is exactly to get information from the first layer A to the second layer B. We're not trying to do any transformations again, because basically we know that getting transformations is easy once we can do representation. So let's just step back, think about representations and see exactly how can we figure out what are these weights, omega ji, such that when we build such a neural network, we can communicate the information X. So this is going to be my state space for my A neurons. And we want to get that information into Y, my state space for my B neurons. So this is going to now require a little bit of math, and it's going to sort of take us in the direction of seeing what benefit we get out of thinking about representation and transformation in the way that we've introduced so far in the neural engineering framework. So what we're going to do is start by writing down the representations that we have in the two parts of our network. So what do I mean by representation? I mean that we want to define our encoding and our decoding for both of our layers separately. So on the A side, our encoding is going to be an equation we've now seen several times. It's going to say that AI is equal to some GI, which is our neuron model, with an alpha I, our encoder, X, which is our input, right? So that's the state space here, plus our bias current, JIB. Okay, so that now defines our encoding for us. If we want to know how to get that information back out of that population of neurons, namely decode X, we would simply write down something like X estimate is going to be equal to a sum over I of the neurons in that population times a set of decoders. And of course, those decoders are one that we found through learning or that we can find very quickly by doing that least squares optimization. So this tells us how we would represent information in the population of neurons that we've marked A. And now we can say the same thing for B. What would the encoding and decoding look like for B? And unsurprisingly, it's going to be essentially exactly the same structure. So we're going to start with BJ. So now instead of AI, we've got a bunch of different neurons. So we're going to call them by a different name, BJ. And nevertheless, it's going to look pretty much the same, where we have some leak integrated fire model. And similarly, we've got an alpha J, an encoder. We have Y now, because of course, this is the state space that we're representing on this side, and our bias term. And for the decoder, we're also going to do something analogous. Of course, instead of representing X, we're representing Y. So we'll say the estimate of Y is going to be equal to sum over J, the neurons in this population, the activity of those neurons times some decoders for those neurons. And we could find them exactly the same way that we've seen finding neurons for X, of course, because the fact that we call it X or Y doesn't really matter. But what we really want to do ultimately, as I mentioned, is figure out how can we calculate this omega, right? That's really what we want. Right now, we're stuck with these decoders that let us extract information from B or let us extract information from A. And what we're going to do is a little substitution trick here. So ultimately, what we want to figure out is what are the weights that are connecting A to B? And this means that we want B to basically be representing X, right? That's really what a communication channel says. It says that I'm going to want my Y to be equal to my X. Right? So it would be saying that whatever's in Y is the same thing that's in X. If we stick some signal into X and it fluctuates in a certain way, we want to be able to decode that same signal out of Y now instead of out of X, because we've communicated the information from X to Y. Now, of course, when we are looking at this population of B neurons, we don't have direct access to X. But the thing we might have access to is X hat, right? So the reason we might have access to that is because that is something we know how to decode using our decoding equation over here out of all of these neural activities. And we know that we're basically sending all of these activities from A to B through all these connections. Okay, so what does this mean? Well, it means that we can go back to our encoding equation in the B neurons. So we have BJ is equal to GJ alpha J, EJ. And now instead of Y, I'm going to write down X hat, because that's something that we think we should be able to get out of the activities. We know those activities can be sent. And then finish off my encoding equation. So, okay, we've got our encoder written down in a form where, yeah, this looks like something we should have access to. And in fact, we can now start doing a substitution, right? We know that that X hat is equal to a sum over I of the AI DI. So we can write out this equation one more time by doing that substitution. So BJ is equal to GJ alpha J EJ sum over I AI DI. So that's my X hat plus my bias term. And the rest is basically rearranging. So we can take a quick look at everything in there. And essentially what we're doing is a bunch of multiplications. We're doing a sum over I, and then we've got our AI. So really what we're going to do is essentially group all of the terms that are not A, because basically all of the other terms are static. So my encoders stay the same, my alphas stay the same, my decoders stay the same if I'm always trying to compute the same function. And the one thing that's changing over time is A. So let's rewrite that part to look like a sum over I of my, sorry, that's my alpha J, my J encoders, my DIs, right? And then that's all going to be multiplied by AI. So what we've done is essentially defined a weight matrix, omega JI. So for every connection going from the pre-population AI to the post-population BJ, we have a weight, which is, a bunch of these elements multiplied together. So we've got the gains, the encoders, and the decoders multiplied together. And if we multiply all those things together, that gives us a fixed weight matrix, right? So that's this weight matrix that we were looking at over here. And then we just multiply that weight matrix by our activities, and that determines the current, plus the bias that's going into these neurons B. And then we can use this decoding equation to actually see if whatever activities we've got in B now, if we decoded those, what does Y look like? And then we can compare Y to X and say, have we successfully actually computed a communication channel? And the nice thing is here, we can be pretty confident that we will compute a communication channel because all I've done is math, right? I haven't introduced anything weird. We already know that this one approximation up here works pretty well. And if we want it to work better, we can add more neurons. And everything else is just substitutions and, using all of this theoretical structure we've introduced in terms of encoders and decoders and gains and biases to define what looks like a pretty standard neural network, right? So right now, all we've really done is said Bj is going to be equal to some nonlinearity, which is given a current, and that current is just a sum over omega ji times a bunch of activities coming from the previous population and a bias, right? So that now looks just like a normal equation that we see whenever we write down things about neural networks. The difference being that we know how to analytically construct and find these weights, right? So this is what we meant when we were saying, hey, deep learning is great. It gives us a way of learning these weights. Through backpropagation, that's definitely true. And what we've introduced here is another way of learning these weights, right? A way where we can basically specify some high-level function, in this case, a really simple function, right? All we did was say that we want y to equal x, but there's nothing that really depends on us having chosen that function when we look through this derivation that we've got here. All right, so I think this is kind of one of the neat aspects of the NEF, thinking of the weight matrix in terms of these two other components, the encoders and the decoders. And the gains, you can always wrap the gains into the encoders if you want. And in some ways, this is one of the more sort of useful and insightful elements of the NEF. So I'm just gonna sort of hammer it home a little bit by basically showing you exactly the same derivation again, but written out in much neater handwriting than what I have shown you on that previous slide. All right, so here's the standard sort of NEF derivation of a set of connection weights. You define the representation of both populations. So there we've got the A representation on the left, the B representation on the right, right? Exactly the same thing that I just did on the previous slide. We can think of this part as the encoding, right? So all we've done is define a current. The current's going into our neuron model. This is the standard way that we tend to define that current with our encoders. You'll notice that I've written it here in the general form where I've bolded my E's so that, that's potentially a vector, or that's potentially a vector, and so on. But these are, of course, very similar on both sides. Then we define the computation we want, right? Here I'm defining, again, the same computation. Let's just say we want y to equal x. But as you can imagine, we can make that any y equal to whatever, x squared, x cubed, that weird function that Terry typed in, what have you. And then we substitute our estimate of x, or the function, right? Whatever that x, the thing on the right-hand side happens to be. And we just substitute that into our encoder for b, right? So I'll do that on the next side. So here we're saying y equals x, which means we have an estimate of that x. We then substitute into our encoding equation our decoder, right? So this is x hat right here. And then you can do a little bit of rearranging, and essentially you end up into the standard neural network equation where we've got some weight matrix times the presynaptic activities, and that determines what the postsynaptic activities are. And in all of these cases, all we're doing to find that weight matrix is multiplying our gains times our encoders times our decoders. And again, when we compute different functions, it's really these decoders that are going to change. As we just noticed, the second principle of the NEF is just basically saying, okay, pick an alternate set of weightings that don't give you an estimate of x, but they give you an estimate of some other function, right? So really these decoders can change depending on exactly what we want to do in our circuit. So this is a perfect place to stop and throw things back over to Terry and let him take you through building example circuits like this.
We're going to start a new example. So let's save this now as example 6. And all that we're going to have to do is, so in this example, we sort of made an output that wasn't a group of neurons. What we're going to do instead is we're going to make a second group of neurons. Just for simplicity, I'm going to go delete all of this stuff. Good. We're keeping this bit at the beginning. Maybe we'll cut it back down to 50 neurons. And all we're going to do now is we're just going to make a new ensemble. One. That appeared. That's going to go there. And all we have to do is say, make a connection from A to B. Now, just like I commented before, whenever you make a connection in Nengo, there's automatically a synapse involved, and there's an automatic assumption that the function, that if you don't specify otherwise, the function it's going to compute is the identity function. So if we just go ahead and do that, now I can pull up my value plot. Let's change this range back to -1 to 1. And I'm going to pull up some spikes. Why not? And I'm going to run that. And I'm going to go ahead and change my input. Whoops, oh, my input range is too large. Let's go my input range back from -1 to 1. Here we are. All right, so what have we got here? I'll pause that, go back in time a little bit, and take a look at what we're seeing here. So first thing I want to notice is that yes, it is doing what we wanted in that it is computing an identity function, like the value that's being fed into A. So we have some neural activity in A, we have some neural activity in B, a weighted sum of that activity gives us this value. That's saying, okay, yep, we can decode out something from there. Here's the neural activity in B, we're doing a different weighted sum, and we got to that, and we're hey, look, these values are pretty much the same, right? So this is representing, it's passing its information along, it is a communication channel. But a couple things I really want to notice here. So first of all, what's actually happening in the simulation is we have a bunch of neurons here, we have a bunch of neurons here, and we're just doing the strange math that Chris was showing in order to compute the connection weight matrix between A and B. Right. But you'll also notice that even though we're passing the information along fine between A and B, the neural activity between A and B is not identical. Right? And this sort of makes sense because whenever we generate a group of neurons, we randomly generate neuron properties. So the neurons in A and the neurons in B have different properties, different gains, different biases, different tuning curves. Indeed, they don't even have to have the same number of neurons, right? So I could have, I don't know, 70 neurons in the first one and, I don't know, 30 neurons in the other one, right? Oops, there we are. All right, so we can have different numbers of neurons, that's fine. That's going to change how accurately each of them represent the identity function, but they're still going to do fine. So that means when you do that math, you don't end up with something simple like, oh, the first neuron in A is connected to the first neuron in B, and the second neuron in A is connected to the second neuron in B. You don't end up with something like that. You get this, a much more interesting weight matrix. Of course, given the fact that we've introduced these tools of whenever you make a connection, you can change the function that's being computed. We can, of course, go ahead and do that as well. You can say, all right, return x squared. And now when we make this connect function, we say function equals square. Okay. So now exactly the same sort of math that Chris was just showing. All we're doing is we're changing the optimization, changing what decoders are being used when computing the connection weight matrices between A and B. And now we are computing the square. Is there anything else I was supposed to show there, Chris, or is that the example?
That's the example, yeah. It's surprisingly straightforward in some ways.
Well, one of the things that we tried in Nengo is to make sure that this sort of thing that we do very often, you'll notice actually the examples have been getting almost like less code as we've been going through. That's because this sort of thing is so common that this is what we optimize the Nengo syntax to be about.
It might be useful to point out too that when you define functions, we've been giving these sort of analytic examples, but you can also define functions with just a bunch of points, right?
Let's do that example too, because that is a really important thing, because the only place this function appears is in that optimization to find the decoders. And that optimization is just over some space. And so what's happening internally is the system is taking this function that you've defined and sampling that function. So generating a bunch of random x values, calling this function on it, seeing what the outputs should be, and then in the background, spitting up a little tiny neural network of just this group of neurons, feeding into that neural network all of those different sample inputs, recording the outputs that come out of that system, and then using all of that data as the optimization to find the correct decoders. Right. But we can bypass that process. So for instance, if I want to compute the XOR function, so just as sort of a standard example of a nice simple nonlinear function, first thing I'm going to do is I'm going to show that this works in this communication channel works in 2 dimensions. All right, so I'm going to change A to be 2 values. Now my stimulus now needs to be 2 values. I want B to be a 2-dimensional vector. Okay. And okay, first I want to show this works as the identity function. So we will get rid of this. Okay. So first of all, the communication channel works fine with 2 values in it. So that should not be, and that's just, it's kind of nifty that it works, but hopefully isn't a surprise with the math. Right. If if I'm specifying my own function, then I can define any function that that I want in here. It doesn't have to go from 2 dimensions to 1 dimension. So let's do 2 dimensions to 1 dimension. And let's do this as the classic XOR function, just because this is sort of a common function that people might have sample data for. So what do I mean by that? I generally have a range of values between -1 and 1. So what I'm going to say is for those inputs, so I'm going to define 4 different inputs that I know the correct outputs for. 1, -1, and 1, 1. Okay, so those are 4 different inputs. And I've got a particular output that I want for each of those. So I want, say, for the first one, I want that to turn into a 1. For the next one, I want to turn into a -1. For the next one, I want to turn into a -1. The next one, I want to turn into a 1. Okay, so for those that are familiar with the XOR function, I'm just using -1s and 1s instead of 0s and 1s, but it's the same idea. For this example, what I want to do is I just want to show the syntax for, instead of defining a function, I just have some data. Please just use this data as what to do the optimization over. So the syntax for that is, when you make the connection, we need to say that the eval points is the inputs. So that's the points at which the function is going to be optimized. Okay. And then instead of giving it a function, we say that the function is the outputs. Okay. So that's the syntax for, just defining some data and saying, hey, just do the optimization over that. And then just to see whether that works, if I feed in a 1 and a 1, I get out a 1. If I feed in a 1 and a -1, I get a -1. Yay, yay. So it's doing a perfectly good job of doing that. Since it was only optimized at those points, it's not really clear what it's going to do in the middle. It's going to do something in the middle. And we generally find with these sorts of systems that it does some sort of smoothed version. If you have outputs that are near the points that you've specified, you'll get something that is near. Okay, but it will generally be a smoothed version of that function. Any other things I should mention in there, Chris?
Maybe worth just mentioning that, of course, you've given an example with 4 inputs and 4 outputs, but of course those inputs could be images and the outputs could be classes, and you can do pretty much anything you want, right? It's just a bunch of data, as people in machine learning are more used to, often having kind of a black box technique where you just have the inputs and outputs and you let the neural network do everything else. That kind of approach is definitely something you can take here if you want to. So it's worth mentioning that because, of course, a lot of our examples are, x squared and x cubed and these really sort of nice functions, but that isn't really important for the framework itself. All right, yeah, so I'm going to jump back over to the slides here. Let me do that. Okay, so this is the derivation that we saw, and we saw how easy it is in Nengo to basically just let it do that for us. And so now it's probably useful to step back and take a look at the principles 1 and 2 sort of summarized for us. As Terry mentioned, when you look at the actual activity in the A population and the B population, it can look totally different, right? And so we're sort of capturing that in this slide, as well as going through the math and getting another perspective essentially on exactly what we've seen. So suppose we have a bunch of neurons and we've got an input, which is X. This is scalar again, and this is going from -1 to 1. So these numbers up here are just going up and down in a sine wave. We've got a bunch of encoders, right, that are basically projecting from that one dimension into however many neurons we have. So that might be 1 to 100. And of course, that generates these activities in sort of agreement with these equations we have down at the bottom. So, we're taking our X, we're multiplying it by some encoders, and introducing a gain that's adding a bias, that's giving us a current, which is driving our neuron model and giving us a bunch of activities, which we're seeing there in blue and red. So principle number 1 is, well, what if I wanted to represent that information? What would it look like? And the answer is, well, we can compute a bunch of decoders that are going to be giving us some estimate of X. And these would be decoders where we'd write, this little X at the top to remind us exactly what function they're being used to decode. And this is really where we spent quite a lot of time on explaining encoding, explaining decoding, giving examples of decoding, and then showing that as you increase the number of neurons, you get better decoding, and et cetera, et cetera. Now, the next step, once we introduced another set of neurons, was basically to say, oh, well, we can pretty much take that decoding and then do the same exact thing into another population of neurons. So here we're introduced B, right? We've got our encoders again. We've got our equations defining our encoding. And then we've got some neurons that can do a decoding. So this now is going to be our Y, which is going to be pretty much equal to our X, right? That's the thing that we're trying to compute here. And so that's what it looks like if we just think about the NEF as introducing these decoders and encoders and working in the decoding and encoding space. Now, as I mentioned before, we don't actually think that neurons are doing this decoding. And the encoding is something, again, that we don't really think they're doing except maybe at the very first layer. And this is why we could essentially crush together the encoders and decoders to give us a bunch of weights, right? So that's really what we just did in the previous slides, is say, let's compute weights of the kind that people are used to. What does that amount to? It essentially amounts to taking an outer product between the encoder and the decoder, or multiplying the decoder for I by the encoder for J, and that will give us a bunch of weights. And then what we showed at the very end is that, in fact, we can change our X, right? So as I mentioned, these decoders are for computing a representation, but we can change our X to any f of X. And so Terry just gave us a couple of nice examples of that. And all that's going to do is mean that when we're multiplying to find our weights, these are just going to be d to the f of X. And that will give us weights for doing whatever the nonlinear function is that we defined. And because we have such flexibility in the way we write these functions down, we've given a bunch of closed form examples, but you can also just give a list of numbers, as Terry showed at the end there. This turns out to be a pretty flexible way of computing the weights that you need in order to calculate in a neural network whatever function that you're interested in going between two layers. Again, another thing we never assume in this math is how many dimensions we have. As Terry just showed at the end, you can crank up the number of dimensions and quite easily compute new functions. And so that's the last thing that we're going to spend a little bit more time on. So if you'll recall, I started off the lecture today by saying, let's pretend that we want to build an interesting circuit, right? And the interesting part of that circuit was that it was a memory, and that memory was going to have to be able to be cleared. So we wanted to be able to multiply some alpha, hopefully the notation's not getting too confusing, some alpha times some x, right, some state. And both of those things were able to change over time. And because they're both changing over time, that means that we have to do the multiplication on the fly. But we haven't explicitly seen how can you do multiplication. And that's what we're going to show here. So if you look at this picture down here, what we've got is basically two sine waves of different frequencies, right? So you can see these sliders going up and down at different frequencies. We've plotted those as being x1 and x2 in a state space down here. And so you get this sort of funky pattern where this thing is moving around through the state space. Now, using exactly the same principles that we've seen, we can take that set of inputs and project them into our neural population, and we know that we can represent them well. So this is showing the representation of that two-dimensional space in A. And these are all the neural activities and spikes that are coming out of A. We can then decode, we can define some decoders which are computing some function, right? And so the function we're going to compute here is x1 times x2. And the reason that we're going to do x1 times x2 is because that's exactly the thing that we needed in order to control our memory, right? So we'll come back to this in the next lecture, but we're basically setting ourselves up for success, right? Now, why do we think that this is actually doing multiplication? Well, if you look at this function, you'll notice that essentially every time you're crossing an axis, right, meaning that either x1 or x2 is equal to 0, that's going to be the same time you're crossing an axis over here, because if you multiply 0 by any number, it's going to be 0, right? So that's at least giving you a hint that it's probably doing something a lot like multiplication. And then last but not least, instead of just decoding that out of this population as we've done here, we can send that information to a second population, right, B, and decode it out of B. And of course, we get exactly the same sort of patterns that we were seeing in the direct decoding here. So now this is an example where we're computing some omega ij, where that omega ij happens to be using decoders, which are doing x1 times x2, right? So ultimately, we basically have just a bunch of connection weights. Okay, so this is another example like the one that Terry showed, where we're taking two-dimensional inputs, we're computing something over time, but here it's this interesting nonlinear function, which we have reason to think is going to be useful for doing control, and in particular, it's going to let us eventually erase the memory. So the last thing that we want to do is talk about learning, right? So we kind of have done this funny thing where we introduced principle 1. We said, how do you find those weights? Oh, look, you can learn them, or Nengo can just find them for you by doing an optimization problem. And now we've gone back to using that optimization technique all the time. But as we mentioned, one of the things we often care about for neurobiological systems is understanding online learning. Like, how could you learn these functions on the fly? And so we've shown you how you can calculate these weights, but we also want to know, how are we going to learn these weights? And that's going to be the final example that Terry's going to take us through, right? So he'll take us through multiplication. He'll let us switch that up to whatever function we want. And then at the very end, we'll come back to this learning rule, where, of course, we had an error, right? And we've defined this learning rule originally in terms of finding these decoders. But we know that in a neural circuit, we don't actually have those decoders, right? I just said we don't think that the encoders and decoders are really sitting there in between two populations of neurons. So what does that mean? Well, not a whole lot, because all you need to do, since we know that the connection weights are equal to the decoders times the encoder, is we can multiply both sides of this equation by our encoders in J. So just multiply by EJ on both sides. And now we've got a learning rule which is actually telling us how to change the weights at every point in that weight matrix in order to compute whatever function is being, which we're getting information about through this error, right? So the first example we saw, this error was equal to, x minus y, or actually at the time it was x minus x hat, because we were just doing a decoding right of the population. But if instead we have x squared minus what is ever coming out of y, right, then we're going to be learning connection weights, which are trying to compute that function x squared. Okay, so hopefully this shows how we can kind of come 360 and say, oh, once we've got this encoding and decoding way of thinking about what's going on in connection weights, doesn't mean that we're stuck in encoding and decoding space. We can use that if that's the most efficient kind of optimization we want to do, and we know exactly what functions we're trying to compute. But if we don't know what functions we're trying to compute, and maybe the system is generating sample points on the fly, then we can use something like this learning rule. So this is, again, that PES learning rule, and actually learn those weights on the fly in order to learn how to perform a new function. And this is exactly what Spawn is doing when it's doing the reinforcement learning example. At this point, I think I'll turn it back over to you, Terry, and you can sort of step through those sort of 3 different examples in Nengo.
All right. So the first thing that we wanted to show was this multiplication example. Like the example that I just did with the XOR, some people might be recognizing that we're actually pretty close to that already. Because if I represent the XOR function in this way with -1s and 1s, this is actually also multiplication, right? -1 times -1 is 1. -1 times 1, -1, right? Each of those examples, those are just 4 sample points of multiplication. Right? If I want to actually do multiplication across that whole entire space, then I should probably go ahead and just actually define that function itself. So define product x, turn x0 times x1. So that's actually the full function I want it to approximate. And then instead of specifying those points, I'm going to say function is product. Okay, let's save that as a different file name. 7, save, there we are.
It might be helpful to point out here the fact that Nengo sort of knows when you send a two-dimensional function or two-dimensional vector into that function to call them x0 and x1 and so on and so forth.
Instead, this x that is coming in, that's a vector. And if you want to refer to the individual elements in that vector, you have to use the Python syntax for referring to elements in a vector. If you have things of the wrong dimensions, so for instance, if b was dimensions 2, then Nengo will yell at you and will say, hold on a second, well, the things are the wrong shape. Right? And that's because this function is returning 1 value, but if b is 2 values, then there's a problem. Right? So if I wanted to do 2 values, well, this could be a function that returns 2 values. So maybe it also returns x0 plus x1. That could be the second value. But we're going on to anything more complicated than that. Let's do this one example. All right, so if I do that and I run that, we should have something that does multiplication, but we don't quite. All right, so things are in the right direction. All right, so if I set feed in -1 and -1, I get 0.5. That seems wrong. No, it's in the right direction, but something seems wrong with this calculation. What's wrong with this calculation? So this is going to be an important thing to keep in mind whenever you are building models with Nengo, because about 90% of the time when you're implementing something with Nengo and things are going wrong, the problem that's happening is exactly what we're seeing right here. You will find in this situation that it seems to be very good at small numbers. So for instance, it's being really good at sort of -0.2, -0.2. Okay, this is somewhere in the right range. It's really good at those, but it seems to be having problems when we get up to these values of like, well, what's 1 times 1 times 1 times 1? 1 times 1 is not 0.4. The difficulty is, and the thing you always need to keep in mind is, what's the range of values that this is being optimized over? Right? We have this radius parameter. We are currently optimizing these connection weights over an input that is assumed to be a unit circle. The 0.11 is way outside a unit circle. So that's why it's being very bad at these sorts of extreme values. Okay.
The XY graphs might help make that obvious, I suppose.
Oh, right. Yes, that's one way we can plot that. So if I plot the XY value plot here, all right, so this is what that group of neurons A is representing. All right. So this is the point being represented. This point, 1, 0, that's inside the unit circle. That's fine. But if I go to the 1, 1, the actual point that I'm trying to feed in is the point way up here. It's ending up, when I do the decoding, representing a value that's in here. Okay, and that's because it was only optimized around this unit circle. There's no reason that it would be good at extrapolating to points outside. And generally what's going to happen is it's going to end up almost doing some sort of soft normalization. It's going to end up representing a value that's maybe not necessarily inside the unit circle, but at least closer to the range, the space that it was optimized over. If we want to improve this, there's a couple different ways we could do it. One is we could generate samples across this whole space and do the sampling ourselves. Another way that we can do it is just change the radius. So if I change the radius up to, say, a circle of radius square root of 2, then that should include the 0.11. So if you're going to go up to, I'm an engineer, so I'm going to call the square root of 2, I'm going to call that 1.5. That's close enough. And now, if I go to that point, we're much better. We're still not seeing this be coming up perfectly. So that could be that I'm using so few neurons in this output population. So let's try increasing the neurons there. Probably also try increasing the neurons here. And now we should have getting better and better at these points. In general, there's a bunch of proofs where it's as long as you crank up the number of neurons, you can make the error arbitrarily small. So that's computing a product, and always watch out for that radius issue. I just want to also show, so we normally, at this point, if we're doing sort of live presentations, we stop at this moment and sort of get everyone to make up your own function, and let's go try implementing that function. So please go ahead and try making up your own function and doing that. I'm going to try implementing cosine of the first value times the sine of the second value, just to pick some weird function. Okay, I'm going to import in order to get access to the sine and cosine. I'm going to go do that. And now I'm going to say, all right, I'm going to say my function. And my function is going to be the sine of x0 times the cosine of x1. And that is going to be my function. Okay. And this, what we're sort of highlighting here is, look, the actual complexity of the code in here doesn't really matter because it's just going to get used to do this optimization. Of course, now that I've picked this function, sure, just trust me that that's the right value. I hadn't quite thought that far ahead about how to check that. Although this is actually kind of a nice example that there is a nice way to check, to get Nengo to check, okay, what would the actual performance of this sort of system be? Okay. So at the moment, I just sort of have to trust, all right, it's doing some optimization. It seems to be doing what we want, maybe. But one thing you can always ask Nengo, and this is really useful for debugging, is, hey, look, let's just take part of the model and just, don't do that in neurons, just compute the function. And that's useful for debugging because, maybe I'm seeing weird behavior and I'm not sure whether the neurons are doing a bad job of approximating the function or whether I've typed in the function wrong. But if you want in Nengo to say, hey, just ignore neurons, just go ahead and treat it as normal code. We have a special neuron type in Nengo called direct. And that's saying, look, forget this number of neurons thing. Just forget radius, forget all this sort of weird optimization stuff. Just throw out the neurons in this group here and just compute this function. Okay, so now we can see what would the ideal system be. Okay. And that's got pretty much the same behavior. Okay. So you can use that as a way of confirming whether or not the system is doing what you expect. You'll notice that A now no longer has any spiking going on, and the value being represented is sort of this perfect. There's no spike noise or anything in that. But that's a useful debugging tool. All right, so we've defined multiplication. We've sort of shown you that, go ahead and pick your own functions, your own strange functions. Certainly, some functions it's going to be better at optimizing than others. So for instance, well, we saw with the one with the, if it's x is less than some value, course, now we're in 2 dimensions. So I don't know, let's say if x0 is less than 0, return x1, else return x, negative x. Let's do, I'm going to do this function. Keep changing my mind about what function I want to do. Let's do this function. Okay. So this is going to be a function that is kind of tricky for neurons to do. All right. And I'll say a little bit why I mean that. So the moment I'm running it without neurons, just to sort of get a sense of what this function does. And this function is saying, all right, you know, if, so these are my values, x0 and x1. The blue line is x0, the green line is x1. This is what's coming out of the system. And as long as x0, so if x0 is negative, then it should always output 0. Okay, so x0 is negative, it's still outputting 0, but the moment x0 becomes positive, now it should be outputting whatever x1 is. Okay, so now, good, no matter what this is, that's happening. Now it cuts down to 0. Kind of a weird function, but totally legit to do. If I ask neurons to approximate that function, get rid of this direct mode thing, and I go and run that. Okay, if I play around, so I'm going to put this up at 1, and go and play around here, you'll notice it's not perfect. It's doing something. You know, it's not outputting exactly 0, as it should be right now. And then I go up here, and now it's you know, it's not doing quite as well as I would like. That's entirely to do with then the number of neurons and neuron properties and how well those neurons are at approximating that function. I can, of course, increase that again, increase my number of neurons to go ahead and do that. But that's the sort of thing that you would expect to see. So when you're implementing your own function, try it with direct mode, with the neuron type is direct, just to sort of get a sense of what that function should actually be doing. And then you can play around with switching in neurons and seeing how well it performs. In general, it turns out there is a bunch of math you can do to figure out, given the complexity of the function or what function you're doing, how many neurons you would need of what type in order to get certain levels of accuracy. And the general statement out of all of that is, if your function is well approximated by low degree polynomials, then you need relatively few neurons. If the function starts having needing higher and higher degree terms in something like a Taylor series approximation to it, then it'll need more and more neurons to get the same level of accuracy. All right, bit of a digression there. The last thing I wanted to show was, let's take one of these functions and let's learn it. Because right now we're doing a bunch of strange math in order to find these connection weights. But we started this whole process saying, hey, look, you can also learn these weights using something like the delta rule. In this situation where we're learning a set of connection weights between neurons, rather than learning just on the output, just on some magic output that we were trying to decode out, the learning rule that you end up with when you sort of roll in that encoder, that's a little bit more complicated than a normal delta rule, but mathematically it should be functionally identical, because it is just doing a bunch of substitutions that Chris was showing. So you can think of it very much like the same learning we were doing before, but it's going to need, but the actual underlying details are a little bit weirder. It does turn out to be a nice local learning rule, so it has that sort of, becomes a local Hebbian-like learning rule. So it's got some nice biological plausibility in it, but let's first just show whether or not it works. So I want to go back to a simpler example just to show this working. So example 8. We're going to go back to 1 dimension. Our input set to there. We've got 50 neurons here. We are going to, when we make this initial connection, we want it to when we did it before, we made this initial connection with a bunch of connection weights we all set to 0. We can do a similar thing here, but what we're actually going to do is we're going to say, well, when we initialize this, initialize it to the connection weights that best approximate this function. Okay, so this is the function that always returns 0. If Nengo goes and optimizes on that function, it's going to get a set of connection weights that are just all zeros, because that's the best way to decode a function of all zeros. Right, so that can be a nice quick way of simply saying, make me connection weights that are all 0. Again, in order to do a learning rule, the thing that we always needed to do was some sort of error signal. So I'm going to make my error. I'm also going to do the error with neurons. Okay, because in the real brain, errors need to get represented by neurons. Okay. And now what we need to do is we need some way of computing the error. Okay. Again, depending on your exact situation, there's got to be something that is telling what the correct value is, wherever that's coming from the environment. We will put, but we want to do the similar trick of taking whatever that correct value is and comparing it to the actual value that's happening in B. So we're going to do a connection, same trick as before. We're going to do a connection from B to error. All right, that's just one of these. Again, Nengo is going to go solve for connection weights to go and figure out how this group of neurons can transfer that information to this group of neurons. That's just a communication channel. Now we've got to do what that external feedback of what the correct value is. Since that's going to be something outside of the brain in this case, we're just going to implement that in code. So we're going to call this desired function of x. And we're going to say, let's do x squared. Okay. And then what I'm going to do is I'm going to make a connection from the stimulus to the error, multiplying that by the function. I'm now going to define a function on this connection. This is going to be my desired function. And I'm going to specify a transform of -1. Okay, what the heck's happening there? So first of all, this is a slightly new use of the connection than we've seen before. So we've seen connections from an external stimulus to neurons before. We've seen connections from neurons to neurons. That's all fine. This one, we've got this connection from an external stimulus to neurons, but then I've also added in this function term. And normally in the past, whenever I've added in this function thing, that's been saying, hey, go and find decoders that will approximate this function. Right? That's what it meant when we went from A to B and specified that function. But this stimulus thing does not have neurons. So there's no way for Nengo to go and find decoder weights from this stimulus to go and approximate this function. So instead, what Nengo is doing is, well, okay, this isn't neurons, so clearly you just want me to just call this function. Right? So we're not approximating this function in this case. We're just simply saying, hey, when you pass the information from stimulus into error, first do this operation on it. Okay. So that's just going to be our programming syntax for take this input, go and figure out what the actual desired value should be. We're multiplying it by -1, so this transform equals -1. That's happening after the function is computed. That's because the error is supposed to be the difference between what is being represented here and our desired signal. Okay. All right. So again, as we sort of did with the learning example before, I want to just run that first as it is so we can make sure this error is doing what we think it is doing. So let's maybe also remove some of these plots. I've got B, I've got A, and I've got my error plot. Let's move that as well. Okay. All right, so now what have I got? If I feed in 0, this group of neurons is representing 0. This set of connection weights has been initialized to all 0, so B should also be representing 0, which it is. Okay, and if I go ahead and move this up to 1, all right, so A is representing 1, B is still representing 0 because these connection weights are all 0. And the error is the difference between B and 1 squared. All right, can't really see that it's 1 squared right now, but let's say I set the stimulus to 0.5. Okay, and now this group of neurons should be representing somewhere around minus 0.25. All right, that's the difference between what we're actually getting in B and the square of the stimulus. Right. Now we got to do the actual learning rule to go and adjust these weights to make these weights better. Okay. So again, the trick is that when we define this connection between A and B, we're going to say, hey, that there is a learning rule, and it's the PES rule. Okay, the prescribed error sensitivity rule. We need a reference to that connection, which we'll call C. We have this error population, and then we're going to make a connection from the error to the connections learning rule. Now we get this green dotted line here. Okay. Now, it's a little weird what's happening here, okay, because this is a group of neurons. This is a group of neurons. This is a group of neurons. There is a big giant connection weight matrix in here. And these neurons, there's some, we're doing all sorts of weird, all of the steps in this process are all doing these sorts of decoders and encoders in order to generate connection weights. Same thing is happening with this connection here. And so everything ends up just being big giant connection weight matrices defined in this weird way. And this error signal is also getting fed by the connection weights from here to that. But conceptually, we can think of it as, look, this group of neurons is representing one value, that error, and that error is being used to drive something like a delta rule, actually mathematically identical to a delta rule in the decoder space, even though delta rule, technically, the thing that the delta rule would actually be adjusting doesn't exist in this model because decoders do not exist here. All there is connection weights between A and B. Okay. But because of the math that we just showed, it's safe to think of it as if decoders actually exist. All right, all that said, I'm going to hit play and see whether or not I've messed anything up. All right, if I feed in a 1. All right, looks like I didn't mess anything up too badly. I can feed in a 1. My error gets driven down to 0. Go ahead. No, if I feed in a -1, my output is 1. And if I go ahead and move this back and forth across this space a little bit. Okay. Well, again, let's be nice about it. Instead of feeding in 0, instead of me manually moving the slider up and down, let's actually say feed in a sine wave. Oh, and let's speed up time a little bit. This will be a harder function for it to learn than the identity function, but given a little bit of time, what we should end up seeing is the error should end up going to 0 as it sort of learns these things. Cool, and again, it should converge on the same sorts of connection weights that we're getting with this computed version. We might have to play around with learning rates and whatnot. You might also need to speed up that input a little bit. There we go. Now we're starting to get pretty good error. So that's exactly the sort of process that we can go through. I find it fascinating that in order to implement this learning rule, we needed to have a group of neurons that represented that error. And it's going to turn out as if you want to implement different types of learning, it turns out that by finding different ways of computing that error, you can go ahead and implement different types of learning, unsupervised learning, supervised learning, reinforcement learning, things like that we can all do with this sort of thing by playing around with how this error is computed. Anything else I'm missing there, Chris?
Seems to have covered all the bases.
Perfect. Then back to you, and we're all set here.
All right, thanks, Terry. So you've computed some nonlinear function in a circuit, then we computed like at a simple one, x squared, and then you computed like a weird one, and then you showed us how we could basically learn that inside the circuit. So now we're basically done, everything that we wanted to cover about principles 1 and 2. So to just quickly summarize what we've seen, basically we saw how to build feed-forward computation in spiking neural networks. And so we just ended on a couple of examples where those computations are pretty much arbitrary. They could be linear or nonlinear. We actually saw how to learn them as well. I think it's worth emphasizing that all the principles we've talked about are really quite general. So we've largely talked about 1- and 2-dimensional spaces, but in our modeling, we use hundreds of dimensions if it's needed. We've also talked about fairly simple nonlinear functions, but we did mention that you can define that function essentially with just a bunch of data points. So that can be a really weird nonlinear function that you cannot write down in closed form. And for these reasons, because the principles are general, they've allowed us to scale up to really big models and be able to build things that look kind of like Spawn. We've also dealt with things like heterogeneity in ways I didn't talk about too much, but you will have noticed that all of the tuning of each neuron was different. We were just like randomly picking maximum firing rates and x-intercepts, and whatever we happened to pick was incorporated into the optimization in a fairly straightforward way. We've also dealt quite clearly with nonlinearities over both space and time. So introducing these notions like filtering and thinking about time a little bit more explicitly by having synapses and understanding what changing time constants on those synapses can do. And we've also dealt with noise. This one I think we talked about perhaps the least, but it was clear when we were looking at a lot of those graphs that there was noise in them, and that in fact there was some relationship between the amount of noise and the time constants that we were picking in our synapses. It's also maybe worth mentioning that when we're doing those optimizations, we're also thinking about noise. So if you kind of know what amount of noise you're expecting, you can provide that to that optimizer, and it can actually take that into account. So right now, we're just using all the default values where we're assuming something on the order of 1 to 10% noise. But in any case, underneath, because we're doing these optimizations in the way that we really are accounting for noise. And a lot of the noise is there in virtue of just the fact that we are representing information with spikes, right? So spikes are very sort of discrete and sharp, which means there's a lot of high frequencies that they're introducing. And so obviously we've dealt with those when we're trying to estimate these smoother functions. And so I think that kind of summarizes what we get out of principles 1 and 2, where we started by thinking about representation and just reproducing what the input was. We then moved to thinking about how to compute transformations over that, which ended up being fairly straightforward, just reweighting basically what all the neural activities. Then we saw, hey, we can go from thinking about just one population and decoding stuff out of it to circuits. So we just looked at a simple 2-layer circuit. And what we're going to move on to next time is basically moving away from pure feed-forward computation and introducing recurrence. When we do that, that's where dynamics are going to show up. So we've seen an example of memory. We started thinking a little bit about dynamics there, but in the next lecture, we're really going to focus on dynamics. It's basically all about dynamics. And then the lecture after that is going to be more about scaling. So, how do we go from what we've learned so far to something like cognition, representing concepts and building up, big models that look like Spawn or other kinds of models that really are tackling cognitive tasks. So those are coming up. But in the meantime, I think we will call it a day and thank everybody for joining us once again for the sort of next lecture in the series that we put together here. And I'll also just quickly point out that, we've got our t-shirts on here. Mine's from 2016 and then
I think mine's
Terry's
2017.
2017, some other year. Yeah. You'll notice we've got the whole set. I don't know how that happened. In any case, thanks again for joining us, and we hope you come back for the next lecture on dynamics.
See you next time.